we'd like to do some algebra review, and primarily let's start with the domain. Now remember, the domain means the set of all possible inputs into a function. So if we're defining y as a function of x, it's basically what x values can we use. The input is independent of the variable because I could be using the variables a and b. So it's just essentially what is the input. Now in calculus, we pretty much stick with x and y most of the time. So if I had a function, let's say f of x equals 1 over the square root of 9 minus x squared. Not terribly complicated, but there's going to be some restrictions because we know we can't have negatives under the square root, and we know we cannot have 0 in the denominator. So what we need is an argument, 9 minus x squared, that is strictly positive. So we'll start by saying that 9 minus x squared must be strictly greater than 0. So we'll do our scratch work off to the side. Well, if that's the case, then x squared must be smaller than 9. So the absolute value of x must be smaller than 3. So on a number line, basically, this would give us every value between -3 and 3, not inclusive. So we'd say that -3 is less than x is less than 3. That establishes our inequality. Therefore, we would answer the domain as the interval from -3 to 3. Domains generally will be stated as intervals out of convenience in this class. There are other ways, but for now, that's the easiest. So all real numbers between -3 and 3, not including the endpoints. So that's a fairly simple example. Now let's look at another one. Okay. What if we have something, let's say, that looks like say x minus 2 over x squared minus x minus 12. Now, clearly the denominator being quadratic is going to have places that will cause it to equal 0. So we're going to need to factor the denominator first. So we'll notice the denominator can be factored as x plus 3, x minus 4. Therefore, all real numbers except the values that will make these quantities 0 would be acceptable. It doesn't matter if the numerator is 0. That doesn't affect the domain. So we'd say that x cannot be -3 or +4. So now if we're to state that as an interval, this is essentially the entire real number line excluding those two values. So we would state it this way. -∞ to -3 open, union with -3 to 4 open, union with 4 to infinity. It might seem a little inconvenient, but it's very clear that it's the entire number line with 2 points deleted. Okay, now let's try another one. So now what if we looked at something, let's say, not complicated. Let's say we have g of x is x minus 4 over x squared minus 16. Now, we notice that, again, the denominator being quadratic means I can probably factor it. So when we do so, we get x plus 4, x minus 4. Great. But we also notice both numerator and denominator have a factor of x minus 4 that can clearly be canceled. This leads us to a little bit of a dilemma. Right now, before I do anything, clearly, x cannot be -4 or +4. The comma mathematically means or. But after I cancel those common factors, I would be left with 1 over x plus 4. Now, this statement here, the only number that I cannot use is a value of -4. But over here, I could not use 4 or -4. And as an absolute rule in mathematics, a domain cannot increase. You can do things algebraically to cause a domain to decrease, but you can never all of a sudden come up with new values. So we have a dilemma in how do I state this? Well, the domain is still all real numbers except here, but if I wanted to simply put an equal sign between here, then what we do is we put in a little qualifier and say, these quantities are absolutely equal as long as x is not equal to 4, because we removed 4 from the problem. So we actually give the number 4 a name in this case. It is called a removable discontinuity. And of all of the, we'll call them weird points, of all of the interesting or weird places in calculus, the removable discontinuities are the ones we probably spend the most time on, because algebraically they're not complicated, but they do cause a dilemma. You see, if I try to evaluate g at 4, I would get 0 over 0, and 0 over 0 isn't a number. Non-zero number over 0 we say is undefined. 0 over non-zero number we say is 0. But what if both numerator and denominator are 0? Well, that makes it interesting, but it also makes it impossible, right? We can't have a number where both are 0. So what we do is we say these two functions are identical as long as this one never uses a 4, because algebraically we'd rather work with the reduced one. So this is a common theme in calculus that we will deal with. Okay, now the next thing I want to go over is something called the fundamental theorem of algebra, which in a perfect world you would have spent a significant amount of time on in a pre-calculus class. So I'll state it. The fundamental theorem of algebra. Now there's so many pieces of this, and I'm sure you did many of them because you did a lot of them in your lower level math class. So let's start with the most basic situation. I have an nth degree polynomial function. So we'll call it P of x, P for polynomial. And P of x is a sub n x raised to the nth power plus a sub n minus 1 x to the n minus first, continuing all the way down to a1 x to the first plus a0. The a's are the coefficients, and you notice the subscript matches the exponent. This is a polynomial function, which means all of the exponents must be positive integers. You cannot have a negative exponent. You cannot have a fractional exponent. You can't have roots in general. So in other words, n could be 1, 2, 3, 4, 5. Could be any positive integer, and we'll go all the way down to the a0. Now, any of the a's could be 0. We'll assume that the first one is not 0, otherwise we wouldn't have a first term. So this is an nth degree polynomial function. The fundamental theorem of fundamental theorem of algebra, we'll get the one about calculus later. This guarantees several things. First off, that I can factor this. Absolutely, this is equal to, now I'll start by factoring out the lead coefficient, and I'll write it as x minus r1, x minus r2, all the way to x minus rn, the same n. So an nth degree polynomial has exactly n factors, as you notice. The r's are called the roots or the zeros of the polynomial. Okay, so if I factored a quadratic, we generally would have, x minus a number times x minus another number. Now the numbers can be positive or negative. The r's could be roots, the r's could be fractions, the r's could be anything. So we do know absolutely this factors this way. Now here's where it gets really interesting. The r's can be repeated and the r's can be complex. You see, if I had something of the form x squared plus 1, this is a sum of squares. We know this has no real factorization, yet we also know it does equal x plus I times x minus I, where I is the square root of -1. Everything can be factored. Not everything can be factored into real terms, but absolutely everything can be factored. Now in this class, we're primarily interested in the real things. So these r's can be repeated. These r's can be complex, but as an absolute guarantee, the nth degree polynomial can be factored into exactly n factors. We are interested in, particularly when the r's are rational numbers, in other words, integers or fractions. But we know that this statement is always true. Now, synthetic division is one of the tools that we use in order to break this down into smaller factors. So if you remember things called like rational root theorems, where you looked at every possible factorization of the first and last coefficients, and then you considered all the possible quotients, and then you said, now let me try synthetic division to knock a few of those off, so then I could factor this into smaller terms. Well, by doing that, you were using something called the remainder theorem. The remainder theorem quite simply says, I'm trying to factor this and I want to find some of the factors. So if I took, in general, if I took P of X and I divided it by X minus some number, I'm trying to determine if X minus C is actually a factor or not. Well, in general, when I do this, the simplest way to check it is that P of C is the remainder as an absolute mathematical statement. When I do the longer synthetic division here, whatever this quantity is evaluated at C, that will be the remainder term. Therefore, if P of C is 0, then it means that X minus C is in fact a factor. So let's do a simple example of that. Let's take something that we know is easily factorable. So let's take something like X squared. How about, we'll do one we did earlier, X squared minus X minus 12, and we'll divide that by, let's say, X minus 5. Now, X minus 5 we know is not a factor, okay? So if I do my synthetic division, remember, this is a review of that as well, I write all of the coefficients in descending order, 1, -1, -12. I bring down the first, then 5 times 1 is 5, -1 plus 5 is 4. 5 times 4 is 20, -12 plus 20 is 8. So this gives me my quotient starting with the remainder, therefore the constant term, therefore that's the linear term. So this would be X plus 4 plus 8 over X minus 5. And as a simple check, when you multiply this out to put it over one quotient, you clearly will get that answer. Now, if my numerator we're calling P of X, so this is P of X over X minus 5. If I evaluate my numerator at 5, notice I'd get 5 squared, 25, minus 5 minus 12, that is equal to 8. And 8 was in fact our remainder. That's what the remainder theorem guarantees. So now let's do a similar problem, okay? Let's do one that we know is factorable. So now let's do X squared minus X minus 12 over X minus 4. Now, we already know this factors beautifully. So if we do the synthetic division now, we're going to say, all right, we have 4, 1, -1, -12. So we bring down the 1. 4 times 1 is 4. -1 plus 4 is 3. 4 times 3 is 12. Aha! I got a remainder of 0. That means that I have 0 remainder, 3, 1 times X. So this is simply X plus 3. Well, we know the numerator factors is X plus 3, X minus 4. And also, if we do a quick check, 4 squared minus 4 minus 12 does in fact equal 0. So one of the most useful things about synthetic division in general is you don't perform synthetic division to figure out if something's factorable. No, you actually say, let me take a 4 and run it through the top. If I get 0, then I know it's factorable, and then I'll use synthetic division to complete the process. Synthetic division is a very useful tool, but it's mostly useful when the remainder is 0, because then I have a smaller term. So let's keep going with this. Get that board nice and clean. Now let's suppose we have, let me take something just terrible and nasty. I picked a really good one. All right. So I've got f of x equals 4x cubed minus 6x squared plus 7x minus 5 over 5x to the fourth plus 9x squared minus 14. And I would like to reduce this. Yikes. Now, the degree of the numerator is smaller than the degree of the denominator, so I can't use longer synthetic division. That only works if the numerator is the same or higher. So what I got to do here is figure out, do they have any common factors? Well, I'm going to be lazy here. And you notice if I replace x with 1 on top, and I like using 1 because that means all you have to do is add the coefficients. then I'd have 4 minus 6 plus 7 minus 5. That's 0. That means my numerator, when evaluated at 1, is 0. The fundamental theorem of algebra guarantees then that x minus 1 has to be a factor of the numerator. Here's what I can say with certainty. My numerator is then x minus 1 times something. Now, I don't know if that's useful yet, but notice the denominator. If I replace x with 1 here as well, I'd have 5 plus 14 minus 14, which is also 0. That means the denominator absolutely is guaranteed to be x minus 1 times something. This means I will be able to reduce this quotient by factoring and canceling the factors of x minus 1. So that was the biggest step of the problem, and that was the easiest thing. So now we need to actually do the factorization. So we'll do our synthetic division on both numerator and denominator independently. So let's start with the numerator. I want to see what happens when I divide it by x minus 1. So that means my root is 1. Okay, remember, it's always x minus the root. So my coefficients in descending order would be 4, negative 6, 7, negative 5. So my synthetic division, 1, 4, then add them. 1 times negative 2 is negative 2, then add them. 1 times 5 is 5, and then add them. And that's important. Now let's do the same thing for the denominator. 5. Oh, I don't have an x cubed term. That means the coefficient is 0. Placeholders are critical because I have to have every placeholder all the way down to the constant term. And because there's no x cubed term, I actually need the 0. Then I have 9. Then I'll have another 0. Then I'll have negative 14. Now when I do the synthetic, that'll be 5. 1 times 5 is 5. Added is 5. 1 times 5 is 5. Added is 14. 1 times 14 is 14, added is 14. 1 times 14 is 14, added is 0. So now I will go ahead and write the complete factorization of numerator and denominator here. This term has an x minus 1. The bottom has an x minus 1. So what's left? And that's the remainder. So the constant, the linear, the quadratic term. So 4x squared minus 2x plus 5 here. Remainder, constant, linear, quadratic, cubic. And then after I cancel the common factors, I will simply get what is left. Now there is one more piece of the puzzle. Remember, the domain of this original function cannot include the number 1 because 1 made the denominator 0. But we factored and canceled and removed 1 from the problem. I can now easily evaluate this at 1 without any issues. But 1 was not in the original domain, so therefore 1 cannot be in my reduced domain. So at this point here, we'd say as long as x is not equal to 1. So I throw in my little disclaimer there every time I do that sort of algebraic process. And it's very important because we don't want to lose track of the fact that we have just changed the domain if we don't do that, and you can never change the domain. Now I'm going to show you a couple real simple algebraic tricks that you may never have done or seen that you're going to find very useful throughout calculus. Because to derive anything in calculus generally revolves around manipulation of algebra. Sometimes trig, but mostly algebra. And we work a lot with quotients of varying difficulties. So I want to show you something that you may or may not have done as a kid. So I'm going to start by writing things using the division symbol, which we know is very impractical in general. But if I said I've got A divided by B divided by C, or I have A divided by B divided by C, or I have A divided by B divided by C divided by D. These are the 3 simplest ways I can have a quotient within a quotient. So if I rewrote these using quotient notation, this would be A over B over C, the big bar here. This would be A over B over C. These are not the same thing. The last one, A over B over C over D. And even the best calculus students sometimes struggle with the manipulation of these, and we make them way more difficult than they have to be, because we start employing all sorts of rules that might not actually be rules. They're just things that we think will help us. So in this case here, we know that when you divide, it's equivalent to multiplying by the reciprocal. So this is the same as A over B times 1 over C. Here, this is the same as A times, the reciprocal here would be C over B. And over here, this is the same as A over B times D over C. Now, of the three, the last one is probably the one most people feel the most comfortable with, okay? Because we know when we multiply quotients, we simply multiply numerators, we multiply denominators. Now, it's possible that I have common factors and I could reduce that quotient, but that depends specifically on what the numbers A, B, C, and D are. In general, we know that this is equal to this absolutely always, okay? Now over here, okay, I know that's going to be A over BC, and over here, if it helps you, put over 1, if that helps. And this is AC over B. So I have three very different results, and every one of them we did correctly, and every one of them we did seemingly efficiently. But what if I told you that most every algebraic process you will ever run across in your entire life can be done in 2 steps or 1? In fact, I find most algebraic processes can actually be done in 1 step. And I don't mean doing steps in your head. Doing a step in your head is still doing a step. Not writing it down doesn't mean it's not a step. I mean, any steps you do, if you count them up, most of the time we do way too many steps. We do a lot of what I call sideways motion. Here's the problem, here's the answer, we want to do this. We don't want to be going back and forth, back and forth, back and forth. We don't want to take 10 steps if we can do it in 2. So how in the world could I have done any of these more efficiently? So Mr. Brown is claiming that each of these can absolutely be done in 1 step. Yes. And we're going to look at more complicated problems as well in 1 step. Now, within each problem, I have quotients. In this problem, I only have 1 quotient within the problem, and that's the number B. Excuse me, 1 denominator within the problem, and that's the number B. So if I multiply numerator and denominator by that number. In the second problem, I only have 1 quotient within the problem, and it has a denominator of C. So if I multiply numerator and denominator by C, I know that I'm not changing the value of the quotient because I'm multiplying by 1. Here I have 2 quotients with 2 denominators. So a common denominator would be simply B times D. So I'm going to multiply top and bottom by B times D. This is the single step I'm going to perform in this problem. When I perform this step, A over B times B is A, B times C is BC. Exactly 1 step, same answer. When I perform this step, I'm going to have A times C. B over C times C is simply B. Over here, when I perform this step, A over B times BD, the B's cancel and I get AD. On the bottom, the D's cancel and I get BC. You notice in each case we got exactly the same answer, and in each case we did so in exactly 1 step. We didn't have to rewrite, we didn't have to do all sorts of things. In fact, it's in the rewriting and manipulation that we often make mistakes. Now, let me show you a very simple version of this that you may have done in a lower level algebra class. It's often referred to as complex fractions, which I think is funny because complex means something. And a fraction means you have a quotient of integers. None of these were fractions. These were all quotients of fractions. They were all rational numbers, but none of them were fractions because I had numerators and denominators that were not integers. So let's look at a really simple example of using what I just showed you, because I want to do this on a bigger scale when we have nasty variable statements. So what if we had something like this? We have 2 over 3 minus 1 over 4 over 5 over 6 plus 1 over 8. And this kind of stuff we know shows up all the time in math. Now, imagine that these are variables. Imagine I have multiple variable statements, and I have to try to reduce this because this is not something that I want to work with. So let me show you the traditional approach, the way everybody learned to do this. Start with the numerator, off to the side. I have 2/3 minus 1/4, and I want to put that over a common denominator. So we want to pick a common multiple. Well, since 3 and 4 are mutually prime, meaning their only common factor is 1, the least common multiple is going to be their product. And so I need to make both of these 12s. So I'm going to multiply this one by 4/4, this one by 3/3. This is the traditional way. This is absolutely correct. So this will be 8/12 minus 3/12. You notice I'm not even going to bother writing 8/12 minus 3/12. I'm just going to put them in the quotient right there. Save myself some time. That's 5/12. I can say now that this is equal to 5/12 over something. All right. Now let's do the denominator. 5/6 plus 1/8 is something 6 and 8, a common multiple. Well, I can multiply them, that'd be 48, but I also recognize, hey, I can use 24. That's smaller than 48. 48 would be fine, by the way. In fact, any common multiple will always give you the final answer. But if you pick a common multiple that's too large, then you're going to have to do a reduction later. Now, that's not an evil thing, but we like smaller numbers, easier to manipulate. If you'd used 48, you'll still get the same final answer. 24 just means you'll get there maybe one step sooner. So when I'm looking at this, I need to multiply this by 4/4 and this by 3/3. And here I'll get 20. Did I do this correctly? 4/4, 3/3. Yes, 20 plus 3, or 23/24. Okay, so I got 23/24. Again, if I did that correctly, so now I've got 23/24. I'm not done because now I have a quotient of quotients. So I'm going to rewrite that as 5/12 times 24/23, as we know. Now I can multiply top, multiply bottom, and then cancel common factors. Now, but then I notice that 12 and 24, I can do that. So that's a little more efficient if I do that. And now finally, my numerator is going to be 10. My denominator is going to be 23. If I simply use the fraction key on my calculator, that'd be very efficient. So why would I do this if I have a fraction key on my calculator? Well, because the fraction key on your calculator won't help you the moment you introduce a variable into this problem. The process is the same whether I have numbers or variables, but I can't use the calculator unless I have just the numbers. So we understand this is the answer. We did not waste any steps. I was very efficient. And this still took way too long. So remember the answer, 10/23. Now I'm going to show you how I do it, which is a little different than the textbook approach and the way most of us learned, because the way most of us learned, it's too many steps. It just takes way too long. Plus, there's too many opportunities to make a mistake. I have 4 fractions. What is a common multiple of all of my denominators? I have 3, a 4, a 6, and an 8. Well, I know I could use a 48, but I think 24 would work. 24 is a common multiple of all of these. So I'm going to multiply numerator and denominator by 24, just like we did a moment ago. Now, think of it like this. You're distributing 24 into the top. You're distributing 24 into the bottom. 24 times 2/3, that's 48/3 or 16. 24 times -1/4 would be -6. 24 times 5/6. Oh, you cancel first if that helps. That'd be 20, and then 1/8, that'd be 3, and that is, I believe, our final answer. That took 2 steps because I had to add those numbers together. No matter how ugly the problem is, no matter how horrible I made the numbers, no matter how many variables I put in, 2 steps is the absolute most it should ever take you to do this problem. Yet we filled up a whole page in algebra class. And we made lots of mistakes because in calculus, we're going to regularly work with quotients of quotients where there's variables and things involved, and we want to be very efficient. So we're going to do a couple of examples where that is going to show up. So the next thing I want to go over is a thing we're going to be doing often in a calculus sense later on in the course, but I want to remind you of something that you probably were shown in a pre-calculus class, and it's often referred to as a difference quotient. Now, the name is so generic and ambiguous. Basically, for any function f of x, I want to find what is f of x plus delta x minus f of x all divided by delta x. Delta x would be the change in x. This is something we're going to do very often in calculus. In fact, we do this in calculus 2. We do this in calculus 3. This is a very, very, very common mathematical step. And so mastering the manipulation of the algebra becomes very, very important. Again, this is often referred to as a difference quotient. I'm not really concerned with that name. I would like to be able to do the algebra. So let's start with a simple one, with a really simple one. Let's suppose f of x is, how about 3x squared minus 2x plus 5. I would like to find the difference quotient. Now, here's the whole point of the difference quotient. I want to be able to manipulate the algebra to the point where there's no longer a delta x in the denominator, okay? And that's the key, because right now, I would like to be able to do this if delta x was a 0. Well, obviously, I can't have delta x be a 0 because then my numerator would be 0 and my denominator would be 0. But I would like to be able to do this for any value of delta x and eventually even a delta x of 0, which sounds contradictory, but remember a moment ago, we factored things and canceled common factors. That was called the removable discontinuity. Delta x is the removable discontinuity in this case. So what I'm going to do is everywhere I see an x, I'm going to replace it with x plus delta x. So my quotient will look like this: 3 x plus delta x quantity squared minus 2 x plus delta x plus 5, that's this piece, minus the entire function all over delta x. Okay, so I need to expand this, I need to distribute, I need to gather like terms and do all that stuff. So let's take our time. So this will be 3 times, I'm squaring a binomial, so that'd be x squared plus 2x delta x plus the square of delta x minus 2x minus 2 delta x plus 5 minus 3x squared plus 2x minus 5 all over delta x. Now this quantity here, I need to distribute that 3. So I'm going to be lazy. Rather than rewrite the entire problem, I'm just going to distribute right on top here. So I've got 3x squared plus 6x delta x plus 3 times the square of delta x, and then all the rest of this stuff. And the reason I'm doing that is because now I can clearly see terms that will cancel. In fact, if you notice, every single term that does not have a delta x in it, every term that does not have a delta x in it, canceled. My whole original function just canceled. Awesome. So now what does that leave us with? That leaves us with a numerator that looks like 6x delta x plus 3 times the square of delta x minus 2 times delta x. That's what we have on top, all over delta x. Now, I would be completely done right now, except for the fact that every term in the numerator has a delta x. So there's 2 ways I can go about the next step. I can factor out the delta x, write that step, cancel the delta x's, and then write the result. And that's absolutely correct. But that's too many steps. It's always correct to do it that way. But that's always the longest way to do it. There's an easier way. Since I want to factor and cancel the delta x, simply multiply numerator and denominator by 1 over delta x. You'll accomplish the same goal as factoring. You're just going to get there sooner. You see, when I multiply the denominator by 1 over delta x, my denominator is 1. I'm not going to bother writing down quantity divided by 1. I'm just going to write down quantity. So when I do this process, my numerator will be 6x plus 3 delta x minus 2. My denominator will be a 1. Therefore, this is my answer. And I got there a little faster. Factoring, canceling, and writing the final answer, this is what you're going to get. That's absolutely correct. From an algebra standpoint, you'll find that I'll show you shortcuts all the way through the course that will benefit you. You're not going to get different answers. You're going to get the correct answer just with less work and therefore less opportunity for error. So here's a simple example of a difference quotient. Now let's do one that's slightly more complicated. And this is going to be using some of the algebra we need to master in this course. Get all this ink off of here. Okay, so the last example I want to do, let's say I want to do the difference quotient with f of x is 4 over 3x plus 1. I want to do the difference quotient with this, which is going to make my algebra a little bit trickier. So my difference quotient, everywhere I see an x, I replace it with x plus delta x. There's my f of x plus delta x minus f of x all over delta x. Okay, now the next step. Algebraically, what most people do, they would go to the numerator, do common denominators, do all my multiplication, do all my manipulation, and then as a next step, now deal with the delta x on the bottom, and all of that is correct. But all of that is highly inefficient. I have a quotient with quotients. The two denominators on top, this one here and this one here, their product is the common denominator. So I'm going to just write it out for you. What you want to do is multiply numerator and denominator by exactly this quantity. I want to multiply numerator and denominator by this quantity. If I do that, I will have one single quotient that essentially will represent the final answer. I might have to distribute and gather terms, but multiplying top and bottom by this quantity gets rid of the quotient on top and puts the common denominator I need on the bottom. Okay, so I'm going to erase that. So when I perform that step, this will become 4 times 3x plus 1, because that term would cancel, minus 4 times 3x plus delta x plus 1, because then that term would cancel, all over delta x times, again, the product, which would be 3x plus delta x plus 1, 3x plus 1. If I multiply numerator and denominator by the product of these two denominators, the next step I have this, and you notice I haven't even distributed yet, but I have exactly one quotient. So all that remains for me to do is simplify the numerator. If I simplify the numerator and I did all the process correctly, it should leave me the ability to factor and cancel out the delta x. As I mentioned before, every term that doesn't have a delta x should end up canceling in my numerator. So rather than rewrite the whole thing, I'm going to be lazy and just go ahead and distribute as we speak here. So this will be 12x plus 4, negative 4 times 3, so that'll be negative 12x, negative 4 times 3 times delta x, so negative 12 delta x, and then negative 4 times positive 1, be negative 4. Now notice on top what cancels, the 12x, the 4, and the only thing left will be a term with the delta x in it. So now I have negative 12 delta x on top, delta x times, now you can choose to distribute here or you can leave it. I'm going to go ahead and distribute. It makes it a little bit less ugly because there'll be less parentheses. So 3x plus 3 delta x plus 1 times 3x plus 1. And notice my last step, simply rid myself of the delta x, and I'll have negative 12 over, again, 3x plus 3 delta x plus 1 times 3x plus 1. And that is my final answer. Now, I can't do anything further with this because these are not the same term. But eventually, we want to be able to say, well, what happens if delta x is 0? That's what we're going to do in a calculus sense. And if delta x ended up being 0, I would have no issues in that case. And that's one of the beauties of manipulating the algebra correctly. So this is our algebra review for today. We're going to do so much algebra throughout this course, and I will always give you hints and suggestions that will make it a little bit easier for you as you go.